This is the cover of the 1940 edition of The Boy Electrician by Alfred P. Morgan. And this book was a hands-on book for young boys who were learning about the new science of electricity. It is filled with a wide variety of model building exercises and so on. And what I wanted to do is I wanted to show you an electric motor from this book. So here are pages 308 and 309 from The Boy Electrician. And on these pages it begins a project on how to build an electric engine. And what I'd like to do is I'd like to read to you from this page right here, and I'll give you a blow-up shot of that next. So here's what it says. An electric engine is really a form of electric motor, but differs from the most common form of motor in that the armature, instead of revolving, moves back and forth, like the piston of a steam or gasoline engine. Electric engines are not as efficient as electric motors from the standpoint of the amount of power derived in proportion to the current used, but they make very interesting models. Various forms of electric engine were made before the first practical electric motor was invented. They amounted to little more than curiosities and could only be used where the expense of electric current was not to be regarded. So let's take a close look at this dinosaur from the past and see if there isn't anything here that's usable. First of all, we have a situation where we have two coils, one here, and each one of them has an iron core, and then there is an iron keeper that comes around. This is a pivot point right here, and this is an iron member. And then this is, of course, connected off to a crankshaft, and that's connected to a flywheel. And behind the flywheel, which is not shown, is a small commutator which allows us to turn these coils on and off at the right time. So the way it works is this, is that when the iron member is as far away as possible from this coil would be turned on by the commutator, and it would attract this iron bar over so that it would push on the crank and turn the crank. As soon as it got as close as it possibly could be to this one, it would shut off, and then this one would turn on and attract it back. So you get 2 power strokes per revolution, and it consists of a situation where there's only one magnetic field on at any given time, and it's simply attracting a piece of iron. And because this situation does not have 2 magnetic fields which are interacting with each other, this situation does not generate any current by induction. So in that sense, this little arrangement, as terrible, as inefficient, and as barbaric as it may seem, does allow you to make a motoring mechanical energy torque with no back EMF. So this is at least the beginning of the understanding of the topology that we're looking for, and that is we're just going to turn one electromagnet on, attract a piece of iron, and turn it off, and let it move away then. And that is the topology of building a no back EMF motor. So let's look a little deeper into this and see if we can't find anybody who has taken this beyond the toy stage. So here is a photograph of a model of an electromagnetic engine that was designed and built in 1840, a full 100 years before the Boy Electrician reported on it. And this is essentially the same design as they showed. It shows 2 U-shaped electromagnets, one behind, and then there's a pivot point here and a bar of iron going across, and this is connected to a crank, which is connected to a flywheel. And there's also a commutator system behind. And so what happens is that you can see on the bar on the back, as soon as it's at the highest level like this, the back magnet would come on and attract that piece of iron down. And you can see they're using as a small and as short a stroke as possible, because what they early found out was that the magnetic field only produced extremely strong forces at extremely close distance. So one of the problems with this type of arrangement was that when the forces, the magnetic forces pulling this down, were at their strongest, you were basically at the top dead center or bottom dead center of the crank, which is the place on the crank where you had the least efficiency of energy transfer. In other words, all of your forces were being pulled perpendicular to the shaft, and they weren't being applied tangential to the shaft. You need forces that are going to apply force tangential to the wheel to transfer the energy efficiently. And so what you can see in this geometry here is that when the force gets very strong, it's really just creating a force that's pulling down on the shaft and not actually applying rotational force. And this has been the problem with these systems from day one. Here's an early rotary design by Charles Wheatstone, the gentleman who figured out how to measure resistors using the Wheatstone bridge. But here we have a fixed ring of electromagnets, and these are each stationary. And then we have mounted on a shaft a ring of iron which is mounted eccentrically. As you can see, it's closer to these than it is to these. And so what happens is that when it's just when the ring is just approaching, like this one here, it would turn, this magnet would turn on, and it would rotate the ring around to the point where it would be the closest again. But again, when the gap was largest and the forces were attenuated dramatically because of the air gap, you could get a fair tangential force to draw it in. But as soon as the forces started getting strong in here, in other words, when we get to like this position here, if this magnet was still on, all it could do is, if it just stayed on, it would just come around to this position and lock in place, because all of the force then becomes radial, perpendicular to the shaft. And again, in spite of the fact that this doesn't have crankshafts and other things like this, it still suffers from the same problem that you turn the magnet on when there's a huge air gap, when the forces are the weakest, and that's when you can get a tangential force. And as soon as the gap gets smaller and smaller and smaller and the force gets very, very large, what happens is that it rotates out from being tangential to being perpendicular. And so this motor had the same exact problems as the linear ones that were cranked off to a crankshaft. Well, literally hundreds of topologies were tried, and no one seemed to be able to figure out how to make this type of situation work. Here's a patent from 1885, and this inventor has finally said, okay, this effect is essentially a toy, and so what we're going to do is we're going to just put a doll on a swing and with a little iron bar here, and we're going to put a little bit of a commutator up in the top of the swing here. And so every time the doll gets very close to these, we're going to turn it on just for a very short, brief moment, and it will cause the doll to swing back and forth and back and forth and back and forth. And here is actually a working model of the original device from 1885. And many people came to this conclusion and tried to take it no further. So there were a few intrepid inventors and motor designers that refused to give up on this method of just attracting a piece of iron into a magnetic field. And here's a patent from 1920 showing 3 electromagnets. And basically this is an iron piece which is slidable along this axis, and then there's a crankshaft here. And so this begins to show a topology which has been generally referred to as a solenoid engine. Because basically what he's got here are 3 electric solenoids, and this is the iron keeper in here, and it goes all the way to here, all the way past halfway down and around. And so what he wants to do here, because all of the lines of force are going to be in here, so he's concentrated the lines of force in a very, very short range, and there's a very, very small air gap on this edge here, and so all it has to do is when this coil turns on, this iron piece is drawn up into there to complete the magnetic circuit and to displace the air. Now again, you can see when the iron piece is all the way extended, as it is in this situation, the force at the end of this stroke should be fairly considerable. And since one of these is going to be pulling all the time, at least one of them will be pulling all the time, this motor probably had a fair amount of mechanical energy. And so there were ways of starting to work with these ideas that people continued to work with throughout this entire period. So here we have another patent from 1936. And here we see the radial solenoid engine taken to its maximum development. And so here we have actually 12 solenoids all the way around, and these, so this is the master cylinder and master crank, and then all of the slaves on that radial section are attached to it. And we can see from the commutator symbology here that he has about 3 of these solenoids pulling at any given time. So approximately 1/4 of the cylinders are pulling all the time, and the others are resetting. And actually, if I go out a little bit, you can see in the bottom here that he's actually planning to have 3 rows of this radial arrangement at 120-degree offsets, which you can see here in the crank. So here's the main crank for the one that we're looking at, but then there's a main crank for the next row and a main crank for the next row. And so what we're looking at here is obviously not a toy design. This is designed for the production of real power. And so it proves that not everybody had relegated the idea of the magnetic attraction engine, or in this case, the electric solenoid engine, to obscurity. There were people who believed that this held a promise that other motor designs didn't hold, and people worked on it throughout this entire period. Now, I probably never would have taken the electric solenoid engine seriously had I not run into this man. This is the work of Benjamin Robert Teal, generally known as Bob Teal. And this patent, which issued in 1978, again looks like the kind of radial design that we've seen in the earlier models. And he's got a master piston here and 3 slaves. And he actually has 2 of these next to each other, so this becomes an 8-cylinder engine. And but unlike the other motors, the claims that were made for this motor were really, really quite extraordinary. And what I'd like to do is show you some of that right now. Now here's a close-up shot of Bob Teal in mid-1970s in front of one of his 8-cylinder radial solenoid engines, electric solenoid engines, which he called the Magnipulsion engine. And let me just, this is the cover of a piece of company literature from his company called the Magnion Industries. And on the bottom here he has this quote from Voltaire. And it says, "There is nothing as powerful as an idea whose time has come." So let's go into the company literature of the Magnion Industries Incorporated and find out about Bob Teal's magnipulsion engine, what he calls tomorrow's energy today. Now, one section of this document from Magnion Industries is presented as a question and answer session. And so what I would like to do is pull a few brief excerpts from this section of the document and bring them to your attention. And the first question here in this section is, what is the magnipulsion engine? And the answer is, an engine that is motivated by electromagnets which serve in a manner similar to pistons in an internal combustion engine. It receives its initial power from a car battery. There is a continuous charge of energy without any supplementary source other than the battery. The capabilities of the magnipulsion engine are relatively unlimited. We know it can power automobiles, air conditioners, home power plants, machinery, or anything which utilizes fossil fuels or electric motor drives. And here's question 2. Why hasn't this inexpensive, practical, and powerful energy concept been discovered before this? The answer is, the field of magnetics has not been explored comprehensively by the scientific community. What has been done in this field before the arrival of the magnipulsion engine has been spasmodic. To the inventor of magnipulsion, these forerunners missed the mark considerably by not harnessing the principles now patented in the magnipulsion engine. So here we have direct statements which basically say that he seems to have found the secret, the way of getting the power out of this arrangement of just attracting a piece of iron into an electric coil. He is claiming to have figured it out. And he's also claiming that the amount of energy that comes out of it will not only run the motor, but apparently keep the initial battery charged. So, let's see what else Bob Teal says. And here, question number 7. How does magnipulsion compare to current standard engine concepts? The magnipulsion engine may be described as superior to any other engine concept known to the inventor, including the present internal combustion engine and electrical engines. And again, here is question 15. Can I bring my engineers to discuss business with your company? The answer is yes. Prospective buyers and their engineering staff are welcome. But they must be prepared to see and learn of a new and revolutionary discovery which some in the scientific community consider contrary to established laws of physics and or electrodynamics. And here is question 24. What is the main difference between magnipulsion and other engines which use electricity to power machinery, etc.? The answer, unlike electrical motors, which take a continuous supply of electric power, the magnipulsion engine runs continuously on relatively minute quantities of pulsating current. Here's a couple pictures of some of the working models. And then questions 29, 30, and 31. Does the engine emit any pollution? No, the engine is pollution-free. Is there any noise to the engine when in operation? Negligible. And here's the big bad heresy. Is there any reason to believe that the magnipulsion engine is incapable of taking over for the internal combustion engine and present electrically powered motors? And here's the answer. The principle proving the utilization of energy from magnets has been fully and completely proven in our shop. Magnipulsion is convertible into relatively unlimited horsepower and therefore can be used wherever these other power sources are currently used. So here are some photographs of some of the working models. This was one of the original 4-cylinder units from his first patent. Here is an 8-cylinder unit from the second patent, and so on. Let me just give you a quick close-up here of some of these models. So he had multiple working models of a very extraordinary a magnetic attraction solenoid engine. So here is the diagram from his second patent showing the 4-cylinder radial construction. And so we see that he has 4 electric solenoids, and this is the master piston here and the master crank, and so the other slaves are connected to it. And what we see is that when the crankshaft is at top dead center, the movable plunger is completely inside the coil. And then when the crank is at bottom dead center, which is what it is for this one, it looks like the movable plunger is approximately 50% withdrawn from the system to see what it would do. Okay, here's an example of the kind of motor we just saw from